Hello, welcome to the ITEEA virtual conference. My name is Fred Foch, and I'm going to be making a presentation named What's Your Angle Here? This presentation is going to use the TI Inspire CX2 calculator and also the BBC microbit. Now you can program the BBC microbit using the TI Inspire calculator. So we're going to be learning about how to do that with the objective of building a digital mariner's quadrant. Well, what the heck is that? Well, a mariner's quadrant was a device used to measure the altitude, that's the angular height above the horizon of stars, in order to find a mariner's position on the ocean as they navigated around in the old days before GPS. And so the way that we're going to be doing this project is we're going to be using the microbit and its internal 3-axis accelerometer, and we're going to use that along with a little bit of trigonometry to figure out the angle of inclination of the microbit. And then we're also going to be using the microbit's built-in magnetometer, which can be used as a compass. And so in order to do all this, students need to locate the North Star. Well, we can use the compass to do that at night. And then also, we're going to make a little sighting device out of a soda straw and tape it along the edge of the microbit. And then we're going to measure in real time kind of a stream pulling of the accelerometers and calculate the angle. And so the idea is the students can sight along the straw, find the angle of Polaris, and gee whiz, that's their latitude. And then they can kind of compare that with the known value of latitude based on like Google Maps or something like that. But this is a pretty authentic STEM activity. I think all the letters are represented. We're going to be talking about the science of astronomy. We're going to be using the microbit and the CX2 technology and Python coding. And then there'll be a little bit of engineering of figuring out how to make this sighting device. And of course, there'll be plenty of math as we talk about the necessary trigonometry to figure out our angle based upon these component vectors of the gravitational field. So anyway, it's a pretty fun project. Thanks for joining, and let's get started. I'm going to switch my view to an emulator view of the calculator, and that's pretty much what we'll work with throughout. And we'll describe the project in that view. There's some pages that will help to understand it. Then we'll switch and we'll start doing the coding. I'll show you how to do the coding on the calculator. And then when we're all finished, I'll kind of give you a little running demonstration of how the whole device works. Now, I'm not going to go outside at night to do this, so you'll just have to take my word that you can point the straw at Polaris and it all works. So again, thanks for attending, and let's get started. So I'll see you in the next view. What you're looking at now is the TI Inspire desktop software that emulates the calculator. This is a great way for teachers to use the calculator in their classroom and lead activities using a smart board or some sort of overhead projector. So if you look on the left of the screen, you can see this is a emulation of the calculator, and you can see the calculator keypad that is on the left is just like the one that I'll be using later as I demonstrate this project. The TI Inspire has several applications inside, one of which is a kind of word processor, which is what this particular page that we're looking at. This is a place where you can actually write directions into a document form and include images. Of course, it also has a built-in calculator, and you can graph with it. You can actually do geometric constructions, which we'll look at here. I have one of those in this particular document. You can also do analysis of data and statistics on that data, and there's data collection that you can do inside the calculator. And last but certainly not least is that you can program a microbit in Python on the calculator. So let's get started showing you how to do this. You can navigate this file, which is called a TNS file that we're looking at, and this is a document that you can either find on the Texas Instruments website, or I'll also upload it to the ITEEA website as well. And at the end, I'll give you my email if you're interested in obtaining a copy and doing this project in your class. But to navigate this, we use the trackpad over here and the control key. You can also use the mouse. There's a number of different ways to navigate with the calculator, but I'm just going to press Control and trackpad click to the right, and you see I go to the next page where I have another little document that gives me some background. So this is a little bit about background on the astronomy of the Polaris and the whole activity that we're going to be doing. And one of the things that we need to know is that the night sky is thought of as a celestial sphere. That is a kind of a crystalline sphere with the stars embedded in it. That's the way the ancients used to think about it. And that celestial sphere has coordinates that are spherical geometry coordinates. And so if you think about the plane of the bottom of the half of the celestial sphere, as you rotate around that, there's an angle which is called azimuth. And so the azimuth of a star is kind of the direction that you look, north, south, east, and west, and it's an angle of 0 to 360 degrees. And then there's also an altitude, which is the angle above the horizon. And so this spherical coordinate system then gives you a unique point in the night sky using angles. So a little bit of astronomy background on the celestial sphere and spherical coordinate systems. So as we go to the next page, it now talks a little bit about Polaris itself. So fortunately for European travelers and other explorers in the northern hemisphere, the Polaris is a recognizable star that's very close to the north axis of the celestial sphere, that imaginary sphere that spins on an axis. And so the north celestial pole star, Polaris, then can be used in navigation. And the way to think about this is that if you are at the North Pole, well, Polaris would be straight over your head at your zenith, which is an angular altitude above the horizon of exactly 90 degrees. Similarly, if you were standing on the equator of the Earth trying to find Polaris, you would find that it's on your horizon. So you would have to look at the horizon and point north to see where Polaris is. And of course, that angular altitude is 0 degrees. Now, this happens to align exactly with the concept of latitude. The latitude of the equator is 0 degrees, and the latitude of the North Pole is 90 degrees. So it turns out that the angular height of Polaris, as you observe it on the surface of the Earth, is exactly your latitude. So for example, if you measured Polaris to be 90 degrees above your head at the zenith, well, you'd be at 90 degrees north latitude. And if you happen to be at 32 or 33 degrees, looking at the North Celestial Pole Star Polaris about 33 degrees off the horizon, well, that means that you'd be someplace, around 33 degrees latitude, someplace around, Dallas, Texas, which is where I'm from. And so it turns out that this is a handy way for you to find your latitude in the night sky. Now, our Mariner's Quadrant can't help us with longitude. That's a whole nother story that's really interesting, but we'll save that maybe for another day. So as we move on, go to the click pad to the right, we need to learn a little bit about the microbit. The microbit has a built-in accelerometer. This is a little chip that's actually soldered onto the microbit board, and that chip can sense the gravitational field vector, and it always knows what is straight down because the gravitational field is always directed straight down. And so as you tilt the microbit around, the microbit changes its orientation to that gravitational field, and that little chip detects that. And it breaks that gravitational field vector up into three components, an x, y, and z component. And so if you hold your microbit just normal to the Earth's surface, and so if you were to do that, the x and y planes, or the x and y axes, are in the plane of the microbit card. And so you would register 0 for those two axes, and all of the gravitational vector would be guided along the z-axis. The microbit reports and measures values of its accelerometer in the units of milli-Gs, so 1,000 milli-Gs in 1 G. And of course, a G is the force due to gravity and creates an acceleration of about 9.81 meters per second squared down, negative. And so we use all that information as we work with the microbit. So you can always assume that this vector of gravity of 1g is always plumb to the Earth's surface, and as you move the microbit around, the plane of the card kind of is maneuvering inside of that gravitational field, always responding in the XYZ vectors, those components. So in any case, that's kind of how we're going to use the microbit's accelerometer. It also has a magnetometer on it. So a magnetometer is a device that is sensitive to ferrous materials, and it interacts with the magnetic field around objects. And so, as you know, the Earth's core emits or produces a magnetic field due to the liquid nickel iron core, and that magnetic field, of course, suffuses space around us, and it's an important concept to protect us from the solar wind and that sort of thing, and it's responsible for the northern lights, and so a magnetometer can interact and measure that magnetic field, kind of the way the accelerometer interacts with the gravitational field. And so the magnetometer is also a 3-axis device. You can measure the magnetic vector and resolve it into the 3 components that are all orthogonal to one another, x, y, and z. And so the magnetometer also has a utility built into the microbit that takes those 3 values, and from them it helps you to figure out exactly what your direction is on the compass. And so the compass heading method in the microbit is really just a calculation done on those 3 axes of the magnetometer to tell you what your direction is, what direction you're heading. So we're going to use that magnetometer as well. And so the idea is that we'll use the accelerometer for altitude, we'll use the magnetometer for azimuth. So how are we going to go about doing all of this? Well, it turns out that there's a little model that I've created. I told you that the TI Inspire has a geometry package that allows you to make geometric constructions. And so, like, for example, if you wanted to illustrate the Pythagorean theorem by constructing a right triangle and then constructing squares along each edge and showing that the sum of the 2 base squares is equal to the hypotenuse square area, you could do all that geometric construction in this application. But I'm going to use it to make a model of our system. And so the way that this works is that there is a construction that shows the gravitational vector. So the green vector here is the gravity vector. And the gravity vector is constant. Well, technically it's not. It varies with your location on the Earth based upon the mass and the type of core material underneath you, underfoot. But by and large, to 3 digits of measure, it's pretty constant. And so that force vector, the gravitational force vector, causes an acceleration of 9.81 meters per second squared down. And that acceleration is resulting from that gravitational force vector. And that gravitational force vector has a value of labeled 1g. And so g for the gravitational vector. And so the microbit breaks that up into millig's. And so the accelerometer reports millig values. And so the gravitational force vector is 1,000 millig's. And it is a vector, so it has a sign. And since it's directed toward the center of the Earth, it's negative. All right, so if you look in this little simulation, I have what Polaris will look like. And so Polaris is part of, well, it's not part of, it can be found using the Big Dipper. And so here's my little construction of the microbit. And so if I take my microbit and drag it around, you can see how it works. And so you can see that to locate the North Star, find the Big Dipper, and then take the end of its ladle and take this the length of this segment right here between these two stars and extrapolate that about 5 segments along that line, and that's the North Star. And so what we're going to do is we're going to take this device outside once we've built it and programmed it, and students are going to hold their microbit and look through the straw and use it to sight right at the North Star. Now when they do that, there will be a unique set of x and y components of this gravity vector. And so if we read the x and the y component, and that's unique, those two values are unique to the angle. You see, if I point it straight up, the x value is all 1,000 millig's and the y is 0. If it's held horizontally, the y is all 1,000 millig's and x is 0. And so you can see as I move these, the x and y components change. And I've also made in the simulation here values of the x and y components. And so these are the values that would actually be read from the accelerometer on the microbit. And so as I tilt this, you can see those accelerometer values change. Then I use the arctangent function, I use the trigonometric function arctangent that takes those two components and calculates the angle that has those two components. And so that's what the math of the arctangent does, is it finds the ratio of the y and x components that yields 23 degrees when we take the tangent. So there's a little bit of math here that we're going to be working with. There's some physics of the gravitational field. There's some vectors here. There's the North Star. And then there's the concept that the North Star is also our latitude. And so there's a lot going on here, a lot of things, a lot of discussion points to talk about with your students. So going to the next page, here we see the engineering of how we're going to build this thing. So, we could tape the straw, the siding straw, in any particular direction, but it's just convenient to use the longest edge because it's easier to tape along that longest edge. And also to put the USB micro connector at the bottom. That way the straw, can lay straight along there. And also remember that there's going to be a cable attached here going to the calculator. So it's just mechanically a better configuration to do it this way. But this is all things that these are all things you can discuss with your students of, how do you do this? Because, well, quite frankly, you have 4 edges you could tape the straw to. Are all 4 equal in functionality? Well, I don't think so. I think that perhaps the leading edge of where the gold connector is best because it's the longest edge, so it's easier to align and tape to, and it's the edge that's away from the USB. So this kind of gives some engineering rationale as to why we build it this way. So that's going to be our build. It's all mistake there. But this is going to be our build. This is what you're going to do. It's real simple. Just get yourself a soda straw and a little bit of duct tape and tape that on there. And so that's our build. So let's go to the next page. And now the coding challenge here. So this is the coding prompt that we give to the students. It says, write a Python program that displays the azimuth and altitude of a star sighted using the microbit as a digital mariner's quadrant. To find your location, go outside with your TI Inspire connected to the microbit and use the azimuth, that's the compass display, to find north and point north. Then find the Big Dipper, and the dipper's ladle will point to Polaris, as we showed earlier in that little construction. And this will help you to locate it. And then use the altitude to display to find your latitude. And that's it. That's how it works. So our next step is to actually code this. So let's switch to coding now. So I'm going to switch to a new view of the calculator where we are going to start a Python program from scratch. We're going to begin by creating a new document and naming the Py file. We'll go ahead and put Quadrant in. The first thing we need to do is to go and add the microbit module as an import statement. Once we have the import statement, we can now start to write our code. I need math because of the trigonometry I'll be using. There are some interesting helper functions in the microbit module under commands. We're going to use this indefinite loop that cycles until the escape key is pressed. In order to use that, I need the system module, so I'll need to import that. The clear history keeps the Python shell clear from print statements. This is nice, keeps everything tidy. Once I'm ready to do this, I'll start to access some of the sensor data. I'm going to get my compass heading first. I'll store this in a variable that is an abbreviation for azimuth. Great, now that I have my compass heading, let's start working on getting those X and Y accelerometer values. I'll use get X and also get Y. I'll go ahead and put this in a variable named X, so the return from the method getX will be stored in the variable X. That's my present accelerometer value. We'll need to do the same for the Y, since I need both of them to calculate the angle. Great. Now that I have my X and Y values, I can start to calculate my angle. I'll use A and G as an abbreviation for angle. And one of the things I want is I want to return the value in degrees, not radians. So I'll use the Python method degrees. I also need to use that arctan2 function to return the angle that has the X and Y as components. Arctan2 takes two arguments, the Y and the X, and those are our two accelerometer values. Now, the next thing that we need to do is to kind of massage the angle a little bit. I want to use my microbit in an inverted way. So as a result, I'm going to subtract it from 90 degrees and then change the phase of it by 180. This will allow me to use the microbit in the orientation that I desire. If you want to build yours in a different orientation, those two numbers are going to need to change. You can figure this out a little better by looking at the diagrams for the X and Y components and how they're related to the plane of the board. And then you can just kind of try them out. Now, I want to round this value also so I don't get too much information displayed. I'm going to just round it to the nearest whole number. So I'll use the round function and round it to 0 places. I could probably use integer here, but this is a better method if I wanted to change the resolution of the display. All right, now that I've kind of got this, I need to display some of this on the shell, so I'll use my print function. And I'm going to put a little prompt here so I can keep the variables straight. So I'll type out azimuth for my prompt, and I'll put in the variable azm, my azimuth value. And azimuth is returned in degrees. Remember, I used that Python degrees for my altitude, and it naturally returns for the azimuth. And the degrees symbol is already available under the special symbols key on the keypad of the calculator. I'll do the same thing for my altitude. Now this is going to make a nice little display of the polling of the azimuth and altitude on my calculator. I'll be able to see it as it runs. All right, great. Now since this is running around in a loop, we need to slow it down just a little bit. So I'll go ahead and use a sleep here. And that sleep can be found underneath the commands, and the argument is in milliseconds, so 1,000 will be a second. So let's give this a try. All right, now that we have our program all written, let's give it a try with the microbit. Now, to use the microbit with the TI Nspire CX2, you're going to need to load a special module that is in the Python environment on the calculator. This is typical for Python to have to install modules, and since this is a full implementation of Python, the same works here. And so you can get that Python module along with the TI runtime, which is a file that loads onto the calculator, that loads onto the microbit, that gives the functionality to talk to the calculator. You can get both of those from the education.ti.com website. And I'll show you links to some of those websites a little bit later. But to get started, again, you need to have the module installed on the calculator, the runtime installed on the card, and then you need to have a cable that connects the mini USB of the calculator to the micro USB of the card. This cable is a cable that you can get from the education.ti.com website. And so for a limited time, we'll be lending these out free of charge. Just check out the website to get started. So to connect this, first I'll connect the the micro end into the card, and then I'll take the mini end and I'll plug it into the USB on the calculator. So I'll just plug that in right there, and when I do that, you'll see that the calculator powers the microbit, and my cable is a little unruly here, and let me get this straightened out. And you can see that when it's running, it has a little Texas Instruments icon on here. So there's a little Texas symbol on the 5x5 LED display. All right, now I'm going to use the compass, and the compass requires a calibration, and it depends upon whether your card has been calibrated prior to this program or not. Mine has, so I don't know if I'll see that calibration routine when I run this program. But if I do, the microbit gives you instructions actually scrolling across the screen as to what to do. Basically, you just turn it around in different orientations to allow it to get its measurements from the Earth's magnetic field. This is no different than a lot of cell phones. A lot of cell phones, when you use the compass, require the same thing. All right, let's give this a try. So I'm ready to run this program. To run this program, I'm going to go to Menu, and so I'll press my Menu key, and then I'll go down to Run. So that's number 2. Oops, number 2 here. And under this, I'll see that number 1 is Run. And so I'm just going to choose that. That's how I run my program. And I'll run it, and we'll see what happens here. All right. Well, it looks like my program is working, and you can see that it's displaying the altitude and the azimuth. I'll try to get the screen so you can see that. And now, when I hold my card in the direction that I kind of designed it to be held, which is kind of like this, you can see that the angular height when I point it up is positive, and when I go toward the zenith, remember the straw is mounted right here on this edge. I don't have a straw, so you'll have to bear with me here. But as I tilt it up, you can see that the angle is increasing toward 90 degrees straight up. And so if I was sighting right along this edge, pointing in that direction, looking up at Polaris there, let's say it would be kind of right about there, I would see that my angle is about 32 degrees, which is about the latitude of Dallas there. Now, to get my azimuth, I need to hold the card in a normal position. And so now you can see that my azimuth is 236 degrees, and as I rotate the card, you can see that my azimuth changes, and so I'll go ahead and try to rotate this until it's at 360 degrees, and it looks like right about there. You can see 356 is pretty close to 360, so it looks like north is that way. And so that's how I would then face. I would face that direction, and then I would use my altimeter, so to speak, my clinometer actually, and I would do it in that way. So that's kind of the way the calculator works. That's how our little Mariner's Quadrant works. And you also have a good taste of how to program the microbit on the calculator. And I'm going to wrap this part up, and I'll share with you how you can get started with this project. Well, now that we have finished our Mariner's Quadrant project, I want to show you how you can get involved using the calculator to do Python coding and building projects with both the microbit and the TI Innovator Hub. The page that you're looking at just now is the TI STEM Projects website. This is a great resource for finding projects that you can do with your class, either as a camp or as an enrichment after a particular section of study. If you're interested in doing a camp or a project with your students, if you scroll down here, you can see that there are a lot of different types of projects that you can do. And if you want to reach out to the TI STEM team, click on this button right here, and it'll take you to a little form you can fill out. Of course, you can also just contact us directly at the TI STEM team, and you can see that email URL. You can see that there are many different projects that are available for the Python and TI Basic using the TI Innovator Hub as well as the TI Rover. But in addition to that, of course, is the microbit. And so there is a page for the microbit that will be published soon, and you can get that from the TI Inspire calculator website. And this will be linked off of the TI STEM projects, and you can also email the TI STEM team to get this URL. But if you click on programming from the TI Inspire CX2 website, you can see that it's everything Python on the CX2 and all the different activities that you can do. There's a lot of other modules that we have not talked about, things for image processing and for rover and drawing. There's turtle graphics. There's all sorts of cool stuff. But here you can see is a link for the microbit. And when you click on that, it takes you to the microbit website for the calculator. And if you scroll down to the bottom, you'll see that there's an opportunity to download all the necessary files. And importantly, right here, if you click on this request form, you can get a cable for your TI Inspire microbit right here. This cable will send you one of those. So threw a lot of information at you, and there's a lot of opportunity for you to get involved with STEM projects using the TI calculator and Python programming. Again, I encourage you to send an email to the TI STEM team and check out the TI STEM projects. Again, you have a couple of those URLs and emails in the banner section of the video, and I'll talk to you soon.